All right, so this next video is going to first start looking at making sure you know all of the conditions of Rolle's theorem. So, example 3 says, why do each of the following examples fail the conditions? So you take a look at that first one, and hopefully it's, I'm hoping you see for 2 reasons for sure, actually probably all 3 for that matter, that none of the conditions hold, but most specifically that 0 in the denominator. 0 fits right in the middle. So since you can't divide by 0, it's not continuous. If it's not continuous, it's not differentiable. And also f of a and f of b aren't equal to each other. So this fails all of the examples, but you just pick one. All the conditions, I should say. So you could just say like f of x is not continuous at x equals 0. And done. Okay. Now, next one, this is continuous. And if you try to put in 0, you do get 4 as an outcome, and you put in 8, and you also get 4 as an outcome. But the reason that this doesn't work is because of it's not differentiable at 4, right? So f of x is not differentiable at x equals 4. So if you actually graph this, kind of see what's happening with Rolle's theorem, and there's no guarantee there's a c value. And the thing is, it's kind of like the existence theorem of the extrema. Like, if you don't meet your conditions, that just means it's not guaranteed. Now, by just sheer luck, maybe you make something so there is one there, but that's not a guarantee. And so if I graph this one, so absolute value 1, 2, 3, 4. There's your bounce. And at 0, it goes up to 4. And at 8, it goes up to 4. So you get a very symmetric looking graph about that line, where your f of a is equal to your f of b. But the thing is that even though that's true, this point right there, it's not differentiable because it's a cusp. So there is no derivative equal to 0. So yeah, again, failing the Rolle's theorem. Now here, right, this is continuous. And it is also differentiable because it's just a quadratic. So the issue here, if you put in 2, f of 2, well, 2 squared is 4. Half of 4 is 2 minus 8. So you get -6. And then f of 4 squared is 16. Half of 16 is 8. And then 4 times 4 is 16. So you get -8. So for this particular one, when you're at 2, you said -6. Oh, I don't know why I drew it to -2. Let's try that again. When you're at 2, you're at -6. And then when you're at 4, you're at -8. So you're down here. So, again, f of a and f of b aren't equal to each other. So there's no derivative that has to be equal to 0. Now, could there have been? I mean, I know the behavior of this won't do it, but could there have been? Sure, you could have created a function that did something like this, right? So look, there's one. But the thing is that, it wouldn't have been guaranteed by Rolle's theorem. Okay, so, and in fact, I know my function doesn't do that because this is, right, that's a quadratic. So it's going to do something like this. So there is a 0 derivative somewhere, and maybe it is on this interval, but it's not going to be there simply because of Rolle's theorem. It's just not guaranteed. However, this is the best case scenario. Like if one condition's going to fail, let it be the f of a and f of b, because kind of foreshadowing what's coming, we can deal with that. But if it's not continuous and it's not differentiable, then obviously that's not good. And we want to try to limit what we study to differentiable, continuous functions, because then calculus and all the things that we need to study and analyze actually works. Okay, so another example, very similar to the maybe example 2. So if you want to even pause the video and try it, it's just it's a different way to talk about Rolle's theorem. It says find the 2 X-intercepts. Okay, great. So finding 2 X-intercepts means when is this function equaling 0? So maybe by inspection, maybe by just a little bit of algebra, we know that when is the function equal to 0? Well, it's not really something you can factor. But like I said, but you could still kind of use the zero product property because you have a product of two things, right? Negative 3x times root x plus 1. When would that be 0? Oh, when x is 0 or when x is negative 1. So x is 0 or x is negative 1. So those two x-intercepts sort of become my endpoints, right? My A and my B. So I already know that like f of 0 is equal to f of negative 1. So that's one of my conditions of Rolle's theorem. And then I also know that if I'm in the interval from 0 to negative 1, I realize that my square root will always exist. So I know f of x would be continuous on this interval. So I can say like on this closed interval, f of x is continuous. And then on the open interval, again, because we're not dealing with the endpoints, f of x is differentiable. So I know that the three conditions of Rolle's theorem have been satisfied. So somewhere between 0 and negative 1, there's a value whose derivative is 0. And kind of linking that back to critical values as a critical value. So it's going to be a max or a min. And it says like we showed that, so we know that there's going to be some derivative equal to 0, and let's go ahead and find it. So I don't know if I could just say, hey, it's there, but let's go ahead and just find it too. So let's take the derivative, and again, I don't know why I've got quite a few examples of this structure where it's like a product of two things with the square root, and my only thought is that it came up on like the AP exam one year, and then I just like, oh, what a cool problem, and so then I made like 17 of them. So yeah, I don't know, and maybe it's time to structure some of these examples. Derivative product rule is -3. Leave the square root alone, and then leave the negative 3x alone. The derivative of the square root is 1 over 2 of those roots. Chain rule times a 1, but again, not really noticeable here. Set it equal to 0. And just like the last two times we solved this sort of problem, I think multiplying by this denominator is a smart thing to do. And I might even just pick the whole denominator. Might as well throw that 2 in there as well, right? So everything times 2 square root of x plus 1. So when I take that times the 0, I'm still going to get 0. When I take this times that value, the 2 times -3 is -6. And then you get your x plus 1. And then obviously when this cancels, and I just get -3x. Okay, so that's 0 equals -6x minus 6 minus 3x. Add this 6 over, and this is -9x, and then divide. So it looks like x is equal to -2/3. And again, -2/3 is in between 0 and -1, so it was guaranteed by Rolle's theorem. So my C value is equal to -2/3. Okay, now, and again, what I wanted to foreshadow about this example here, that's going to lead us into something that's called the mean value theorem. And really the mean value theorem, or I should say Rolle's theorem, was just a special case of mean value theorem. And the only difference is that in Rolle's theorem, f of a and f of b have to equal each other, right? Your y values have to be the same. But if you start changing those, then you get a different outcome, but similar concept, and that's what mean value theorem's about.